Now we're going to look at another form of data called an arbitrary arity tree. And as we'll see, this form of data is characterized by having two cycles in the type comments. It'll be the most complex form of data we've seen so far. But don't worry, a pretty incredible thing's going to happen here. Because of everything we've learned about type comments and references and templates and trusting the natural recursion, designing functions that operate on arbitrary arity trees is actually going to be pretty simple. It's only going to be a very little bit harder than designing functions that operate on lists. That's what you'll see as we work through these next couple of videos. So here's what I mean by file system. And again, this could just as well be a photo organizer or something like that. But when I look at the files I'm working on for this class, there's a desktop. On my desktop, there's these folders. And there's a folder called MOOC. And in there, there's a folder called Current. And in there, there's a whole bunch of other folders, including one called Starters. And then there's Week 3. And here's all the starters that you had a little earlier in the course. So what we need to do is to come up with one or more data definitions that can help us represent an information structure like this. Now we're going to simplify it a little bit. We're not going to worry about the actual contents of the files. We're just going to worry about a directory structure like this that has files in it. And for the actual contents of the files, let's just assume they hold a single number. A single integer is all each file holds. If I redraw it this way, then it looks like, or at least to a computer scientist, it looks like a tree. This is an arbitrary arity tree, and I'll say why it's that in a minute. First, let me say why it looks to me like a tree. It's because computer scientists draw trees upside down. We're kind of drawing the roots or something. And let me just point something out about this. What I'm going to say about this tree, or this model of an arbitrary arity tree, is that each element can have sub-elements. So for example, MOOC has a sub-element or a subfolder current, and current has a number of subfolders, and starters has subfolders. But IL starter just has data. It's a file that just has data. And to simplify things for now, we're going to say that the only data it can have is just a single integer. We're not going to model storing the actual contents of the files in here. Now, why is it called arbitrary arity? Well, unlike lists, which were arbitrarily long in one dimension or arbitrarily wide in one dimension, this arbitrary arity tree is arbitrary sized in two dimensions. A given folder or directory, like W03, can have an arbitrary number of elements in it. Current has a number of them, starters has a number of them, W03 has a number of them. So it can be arbitrarily wide. In addition, the structure can be arbitrarily deep. This particular one is 1, 2, 3, 4, 5 deep, but it could be deeper. Remember, arbitrary doesn't mean large and it doesn't mean random. It just means that before we start out, we don't know how big it will be. Now, in order to deal with this arbitrary sized in two dimensions structure that this has, the key thing that we're about to see is that it's going to require two cycles in the type reference graph. Remember, in order to have an arbitrary sized list, we had one self-reference cycle in the type reference graph. Here we're going to see that we end up having two of them. So now let's turn to Dr. Racket and start looking at that. Now I'm in fsstarter.racket, and what I have here is the beginning of two data definitions that can be used to represent arbitrary arity trees like this one. So first there's a structure definition, ELT, which has three fields, name, data, and subs. And of course we have to keep reading to know what that's about. And there's a type element, and it says element is a make element string integer list of element. And an element is an element in the file system. So that's going to be something like, from our picture, MOOC or current or lecture exercises or starters. And what I'm saying here, because we said in the analysis that an element could either have sub-elements or it could have data, I'm saying here that there's data, which can be an integer, and there's subs, which is going to be an arbitrary number of elements. And it says if the data is 0, then subs is considered to be a list of sub-elements. If data is not 0, then subs is ignored. There are other ways to do this where instead of having an element have both fields, in other words, both data and subs, you make two different kinds of elements. I thought this was simpler for our purposes for now. And then what's list of element? Well, list of element is just an ordinary list of type like we've seen several times now. It's just a list of file system elements. Now let's see if this can build up the structure we want. So what I'm saying here is F1 is an element called F1. It has a non-zero data, so it's like an ordinary file. That's why I called it F. And its subs are supposed to be empty. Its subs are ignored, basically, so I just put empty. So that's F1. F2 is just like F1. It's another file. It happens to have the contents or the data too. And F3 is the same. Now what's D4? Well, D4 has 0 for the data, so that means we're going to pay attention to the subs. And what subs does it have? Well, it has two subs, F1 and F2. So that looks like this. And then D5 has a single sub, F3. And then D6 has both D4 and D5. So that little set of examples there builds up this directory structure here. And I think we can see now pretty clearly, it looks like we can build an arbitrary arity tree here. Let's see why that is. Well, if we look at list of element has a self-reference in it. And that's what's allowing a directory's list of sub-elements to be arbitrarily long. That's what lets this list have F1 and F2, and this one have D4 and D5, and clearly those could be as long as they want. Now, in addition to that self-reference, notice that there's a reference here from the middle of the list of element type back to the element type. We've seen that kind of reference before, but hang on, because there's something else going on here. There's also a reference from the element type down to list of element. Now those two references together form what's called a mutual reference. So we're going to label them MR, because you can go from the definition of list of element up to element, and the definition of element down to list of element, and there's a cycle there, a mutual reference cycle. So in addition to the self-reference cycle, which is letting one directory have an arbitrary number of immediate subdirectories, the mutual reference cycle between list of element and element is letting that be arbitrarily deep. So D6 can have an arbitrary number of subdirectories, D4 and 5, and each of those can have an arbitrary number of subdirectories, and so on and so on and so on. And so what you can see here is that these two cycles in the type comments, the self-reference cycle and the mutual reference cycle, support an arbitrary arity tree, a tree that can be arbitrarily deep and arbitrarily wide at any point. One quick note about these arrows and the way you label mutual reference arrows. The way I do it is first I draw all the arrows. Then I label all the self-reference arrows. Then I put my finger on an arrow and I start following it around through the types. And if I ever come back to that same arrow, then all those arrows along the way were part of a mutual reference cycle. And then any arrows that aren't part of a mutual reference cycle and aren't part of a self-reference cycle are just ordinary reference arrows. In this case, where there's just two types, it's easy. But sometimes you can have mutual reference through 3 or 4 or 5 or 6 or more types. And then it's a little harder to get the arrows right. It's very important to get them right. We're going to see it helps us a lot with the templating that we'll do in the next video.